So now let's look at doing the same sort of calculations for basic buffers instead of acidic buffers. We have an analogous expression that is derived from the KB expression, so we can do the same sort of thing. We know that when we talk about our generic base, B, it reacts with water to give us in equilibrium BH plus OH minus. And we know then KB is equal to BH plus concentration times the OH minus concentration divided by the concentration of our base B. Now, in basic solutions, we solve for the hydroxide ion concentration, so I can rearrange this to solve for the hydroxide concentration. The hydroxide concentration is equal to Kb times the concentration of B divided by the concentration of BH plus. And if we take the negative log of both sides, we get the negative log of the hydroxide concentration is equal to minus the log of Kb plus the negative log of the concentration of B over BH plus. So rearranging this, we get the negative log of the hydroxide is the POH. The negative log of Kb is pKb plus the log of BH plus over B. So you'll notice that I got rid of the negative sign. Instead of plus the negative log, I just have plus the log. By taking the log rather than the negative log, I flip these two concentrations upside down, and now they're in the same order they always are, products over reactants. And I think it makes sense to think of it that way. So this is the basic form of the Henderson-Hasselbalch equation. So we do this exactly the same way, except that we're now using POH instead of pH. So this is a little bit trickier because you do have to think about looking at the charts. They give you the pKb on the weak base chart. You have to choose one whose pKb is within 1 unit of the POH you want. And since we talk about pH, you have to switch it to POH. Okay? So we choose a soluble salt of the weak base's protonated cation, the conjugate acid of the weak base. Chloride salts are cheap, they're readily available, and they work most of the time. You want to avoid chlorides if you're going to have silver, lead 2, or mercury in your samples because that can cause precipitations. Any anion from a strong acid except sulfuric will work. So if you want something that works always, choose nitrate. Nitrate will always work and it's reasonably available. I like to use chlorides just because it's only one atom to add in the mass and they're pretty much readily available. Chlorides are cheap salts. So how would you prepare 1 liter of a hydrazine buffer with a pH of 8.10? The pKb is 6.02. Well, the first thing you have to do is find the POH. So the POH is equal to pKw minus pH. So that's 14 minus 8.10 is equal to 5.90. So the desired POH is 5.90 and the pKb is 6.02, so this is a good choice. So we know that the POH is equal to pKb plus the log of BH plus over B. So we can now plug in our numbers. My POH is 5.90. That's equal to pKb 6.02 plus the log of the BH plus concentration over B. So now we rearrange. 5.90 minus 6.02 is equal to the log of the ratio of the BH plus concentration over B, and that's equal to negative 0.12. So taking the antilog or exponentiating, 10 to the negative 0.12 gives me the ratio, my BH plus over B ratio, and that's equal to 0.76. So now I've done my math. Now I have to think about what salts I want to use and do my calculations including molar mass. So I have hydrazine, which is N2H4, and its molar mass is 32.0456 grams per mole. And in this case, I chose as my salt hydrazinium. So I add one more proton to the hydrazine, N2H5, and then I add a chloride. It's hydrazinium chloride, and its mass is 68.5065 grams per mole. So now I have to decide what concentrations will I use. 0.76, just to make things easy, I chose 0.6 molar hydrazinium chloride, that's the salt, and I chose 1 molar hydrazine. Those are always a good choice, anything between 0 and 2. So now I do my calculations. 0.76 moles of hydrazinium chloride per liter. I know that I want to make up 1 liter, and it is 68.5065 grams per mole. So I need 52 grams of hydrazinium chloride. Now I do the same calculation for the hydrazine. 1 mole of hydrazine per liter. I want 1 liter, and its molar mass is 32.0456 grams per mole. So I need to weigh out 32 grams of hydrazine. So now I've done all the math. Now I'm going to write my instructions. So I would dissolve 32 grams of hydrazine and 52 grams of hydrazinium chloride in water in a 1 liter volumetric flask. And I would mix, dilute to volume, and mix again. And that's how you prepare a buffer. So I have one for you to try on the next page. Let's go ahead and do this in your groups on your whiteboards.